All right, guys, our fourth and final part of section 1.5 on polynomials. We're going to be determining today if functions are even, odd, or neither. We actually have not done this before. We've worked with degree, and we've talked about if the degree is even or odd, but not if the entire function is even, odd, or neither. So let's take a look at what this means. And it says this: polynomial equations are odd if every term has an odd exponent on x and it's in standard form. Okay, so if every single term that's in the expression has an odd exponent on x, then the entire function is odd. All right, that's for polynomial equations. And then also if every term has an even exponent on x, then it's going to be an even function. And we're including 0 as being even. 0 is still an even number. It is a multiple of 2, even though it's just 0. All right, so let's see what this looks like here now as we're answering these three questions. So we're going to determine if these are even functions, odd functions, or neither for each of these. So the first problem, we have a degree of 2. So the first term has an even exponent. The second term, though, the way this is written, it does not have an exponent. But remember, if there's a constant by itself, there's an x to the 0 attached to it. All right, and so our first term had an even exponent. Our second term also has an even exponent. So this f of x function is even. Second function, the degree is odd, right? The biggest exponent is odd. But we have a mixture of odd exponents and even exponents. So even though there's two odds and one even, we say that it's neither. They have to all be odd or all be even for it to be an even function or an odd function. All right, then lastly, we have x to the third. Then we have a 2 times x to the first. And again, it's our exponents we're looking at. They're both odd exponents. So it's an odd function. All right, a little bit more about even and odd functions. So the ones we just worked with are polynomials, but not every question is going to be about a polynomial. So all even functions, they're going to have symmetry about the y-axis. So it doesn't have to be this graph, but something like this. Whatever's to the left of the y-axis, we just flip it over, and it's also the graph to the right of the y-axis. And we also say this, that f of negative x is equal to f of x. And all that's saying is if the x values change sign, the f of x values or the y values are going to be equal to each other. So, for example, if this is the point negative 1 comma 2, then this is the point 1 comma 2, right? If the x's change sign, the y's stay the same, right? Or f of negative x equals f of x. Odd functions, so they have symmetry about the origin. That often means they're going to pass through the origin, but not every time. What that means is if we were to reflect, we'll do it in yellow here, reflect the left half of this graph over the x-axis. So it looks like this. Okay, the graph is now symmetric about the y-axis. So if I were to flip this yellow part over, it would be on top of the part that was to the right of the y-axis originally. All right, so again, if I take half the graph and I flip it over the x-axis and then over the y, the graph should be on top of itself for it to be symmetric about the origin. Now, with these functions, let me switch back to white here. With these functions, f of negative x is equal to negative f of x. So what that's telling us is that when x changes sign, the f of x or the y value also changes sign. So let's just say hypothetically this point was negative 2 comma 3, right there. Well, then that means over here, this would have to be the point positive 2, negative 3, right? When x changes signs, y also changes signs for odd functions. All right, so looking at these graphs, we're going to determine are they even, odd, or neither. So this one, let's see, it goes through the origin, but that's not a guarantee that it's odd. We're going to flip this part over the x-axis, so it looks like, try again. That wasn't very good. One more try. Like that. Okay, and if I were to reflect it again, you could see that the graph, it is now symmetric with this portion over here. All right, so reflect over the x, then over the y. So this is going to be an odd function. Next, this is not perfectly drawn, but it looks symmetric about the y-axis, so that's always going to be an even function when that happens. And then lastly, there is symmetry on this graph right here. There's symmetry, but it's not about the y-axis or about the origin, so it's neither. Okay, even though it does have symmetry. All right, lastly, given a table, so we're going to try to figure out, is the function even, odd, or neither? So remember, with even functions, when x changes sign, y stays the same. Okay, so if x changes, the y stays the same. That's for even functions. For odd functions, when x changes, y also changes. So I'm going to put both change signs. So let's look at these two problems here. So I'm noticing these two are the same x's with different signs, and their y's are also different signs. So when x change signs, y change signs. And same thing here, from -1 to 1, when x change signs, y also change signs. So if both of them are changing, it's an odd function. Odd function. Now, this one didn't go through the origin. It doesn't have to go through the origin for it to be odd. It just has to be that when x changes signs, y also changes signs. Now, down here, when x changes sign, our y's stay the same. And same thing here, when x changes signs, y stay the same. So that's going to be an even function. And then that was it for those two. Yeah, so that's it for even and odd functions. We're going to work on memorizing those two and trying to keep straight when is it even, when is it odd. But that's it, guys. Stay flawless.